the Betalike rules, which is consistent with the idea that definitional equality should be representing equational deduction as a consequence of the definitions or just symbolic execution. Okay? So if we take that as our baseline understanding of definitional equivalence, certainly we want that. And this somehow is a different sort of thing. This is a kind of an induction principle. It says every element of the type is the form of a lambda. So in the same way that like mathematical induction says every element of the natural numbers has the form of either a zero or a successor. It's a little bit like that. So I kind of don't want to, you know, I probably don't really want to go there and introduce this as a principle of definitional equality. Okay? However, I will admit it's not like hard and fast rules here. This is like, you know, I'm giving you some feeling. Okay? All right, so that's the notion of the product, okay? And you can see, by the way, that this, I should have said this before, this corresponds a little bit to the rules that you would expect to see for like universal quantification. Because, well, in traditional logic, you don't worry too much about the forms of proofs. But if we said B of x is true for every x in A, so suppress this and just read that as B of x is true for every x in A, then something or other which we suppress in the traditional accounts of logic witnesses that for every x in A, B of x is true. In other words, the meaning is just exactly that it's true uniformly in x. And then that looks exactly like a conventional rule of logic when written like that. And the same here, if we read that as for every x in A, B is true. So if we read that, forget the M itself and just worry about the fact that it exists. If this is true and I have a particular element of the domain, then, well, in traditional logic, we don't worry about how to notate it, but what we get is the fact that n for x, B is true. That is, if I quantify over x and I plug in a particular x, then that instance is true. And the truth of it is witnessed by this application. Okay? And then in traditional logic, because we don't worry about proofs as being objects of study, then we don't worry about when they're equal either, so none of this comes up. Okay, it's a pity, but that's the way it is. Okay, so once you learn logic from the point of view of type theory, you'll never be able to look at logic the same way again, because it will look very kind of broken to you, because somehow half the story has been completely omitted for some unknown reason. You know, that's the way it is. That's part of the advance of type theory, why it's important, why type theory is important, and has made advances in the field that have not been made before. So it doesn't erase very well either. Okay. All right. So that's that. So now let's also look at the sigma type, which is you know, looks sort of formally similar. So the idea is this is a big sum. So we're going to say we have the sum over A of a family of types B of x. I'll write that here. And that's going to be a type exactly when A is a type. So you have a domain of quantification, and B is a type. So the formation conditions are the same. So this is sigma formation. Okay, and then we're going to have the introduction and the elimination. Okay, so the introduction is, what does it mean to have an element of sigma x in A, B? And I can write the x there if I want, just to emphasize the dependence. Okay, so what is an element? Well, this is supposed to be thought of as the big disjoint union indexed by A. Okay, so it's the big sum over the type A of each of the elements of type B of x. So the elements of that type can be thought of as consisting of an index element A. Say, hey, I'm over, this is the particular element of A I'm talking about, and an element n whose type is m for x, b. And in that case, the pair mn becomes an element of sigma, the sum of sigma x and a, b. And this is where another terminological confusion comes up, because the elements of the sum are pairs. So then people say, oh, so we should call this the dependent product after all, because it's a lot like product, except that it's dependent. And that's true, but it's confusing. Okay, so it's the terminology doesn't is a long-standing issue here about the terminology, but I'll just explain to you what that is. So if we're taking this big disjoint union of a bunch of things, if we think temporarily of these as sets, it's misleading. The set theoretic interpretation here is low dimensional, and we're going to be talking about higher dimensional interpretation later. But in the low dimensional setting, these are just sets, so this is a big disjoint union of a family of sets indexed by a set. So these are just the formal notation we have for writing down the elements of that union. So now I want to say that this corresponds, and again, the correspondence, it's a little awkward because it doesn't line up with some textbook exactly, and I'll tell you why in a minute. But it sort of corresponds to an existential quantification, right? It's going to be the idea that, and you can see this nicely when you look at, this is called the sigma introduction rule. If you think of this as an existential quantifier, it says, if I want to show you that there exists an x in A such that b of x is true, then what I do is I exhibit a particular A, that's the witness to the existential, and then I tell you that that particular instance, that B is true for that particular instance. And so you can see the correspondence to existential quantification. In ordinary logic, as I say, the proof objects are suppressed. So the only thing you see is the term, the particular witness. So if you're working in arithmetic, that would be a number or something. And then you would show that that instance of B is true by the rules of logic, and then you would conclude that there exists one. Okay? So that's where that corresponds. Of course, the correspondence starts to break down as soon as you realize, as I mentioned again, to reiterate, in type theory, A can range over more things. Now, the correspondence starts to really break in the next two rules, which are the sigma elim, which I'll 1, and sigma elim 2, and then I'm going to give you an assignment. Okay. All right. So this is what we do here. So what I want to do is I want to invert, okay, the introductory rules. I want to say, well, if you give me an element of the sigma type, you write it like that, what can I do with that guy? Well, the principle of it is that the introduction rule tells us what the elements are. They're ordered pairs. So if I put two things into it, then by the principle of conservation of proof, I should be able to pull those two things back out of it. Okay, that's the idea. So this is so I put M is something that I put into it. We know that ultimately what I put into it must be in this form, so we'll introduce projections. So there are different notations people use. One is pi 1 of M, which is A, and then under the same conditions, we put here pi x in A, b x, and then we will have that pi 2 of M is, and now this is the critical thing, pi 1 for M x b. That's very critical. Okay. So, and then we would have definitional equivalence rules, and if you don't mind me slightly just scribbling, I won't write it all out carefully. It's the obvious ones, that this should be M, and this should be N. And as an aside, the converse of the local completeness would say, if you do this, you should have M, but I won't consider that here as a principle of definitional equivalence. I won't do that, but that's a similar analogy to what we had before. So this is these are the important ones for computation. Okay, now the question is how this looks compared to ordinary logic. And the answer is it doesn't look very good compared to ordinary logic. And this is a spot where the way I like to see it, oh yeah.
So is this like the traditional way of doing it, or is it possible or ever done to write it the separate way, like the CBS version where you say like let?
That's what I'm about to say.
Okay, cool.
Okay. Second. Okay. So here's a collision point. So for me, okay, I'll tell you my point of view. The logic can only be explained as a mode of use of type theory, period. Okay? But people have tried to explain it without the benefit of type theory, and you get into trouble. And this is a spot where you get into trouble, and I'll tell you why. Okay? So suppose we think of this as an existential quantifier. Okay? So if this existential formula is true, that's the way we're supposed to think about it, well, one thing you've got now is a term. a term that takes a proof and turns it into an object of the domain of quantification. So at the moment, let's say, just for concreteness, let's think of A as being the natural numbers. Then what you're doing is you're saying, give me a proof of exists X in A such that B of X, and I'll extract from that proof a term, a number. You can't do that in ordinary conventional logic because the proofs are not objects. Okay, you're not able to even express, this is a non-starter, there's no way to even say this. So this does not correspond to a rule in conventional logic. And this one is only worse. If you make this into an existential quantifier so that what you're doing is you're saying, well, the M colon means this proposition is true, then you're able to extract from it another proof, which is a proof that the quantified formula is true for that particular witness, pi 1 of M. I don't know what pi 1 of M is. For example, M could be a variable. So I don't know what M is. M is not necessarily a tuple that I know. It could be a variable. But certainly pi 1 of X is an element of A such that this formula is true. That cannot be expressed in ordinary logic either, right? There's no way to say these do not correspond exactly. Now, I would argue that these are the correct rules for existential quantification. I need a spot in which to write. I'll go over here. Okay. But they're not the ones you usually get. So what are the ones you usually get? And I'm going to ask you to derive them. The ones you usually get is something that looks like this. It says, well, let's write it as if it were type theory. So we'll do it like this. So if you have an element of sigma x in A, B of x, or think of that as an existential. So if you know that the existential is true, then your reason as follows. You say, well, given x in A, given a proof that B holds for that particular x, because the way you reason is you say, if I know that there exists a number with a certain property, I say, well, let x be a number with that property. And the with that property part means introduce a variable standing for the proof, okay, that you have when you're working in the constructive setting. And then you derive a proof of some other proposition. Okay, this is the typical thing, where that proposition is extrinsically meaningful in the ambient context gamma. And then you say, something or other witnesses the truth of C. And it's a kind of let. There are many ways to write this, but it amounts to something like let x, y be M in N. N, that should have said, excuse me. All right, in N. Okay, it would be like that. That would be your typical, suppressing the proof objects, that would be your typical mode of reasoning in a typical formulation of logic. Your exercise is to show that that's derivable. Okay, so we'll do it like that. So you can get it on the basis of these principles. But these principles are, much stronger. I mean, these are saying, well, they're saying the right thing, okay? First order logic or conventional treatments of logic like this have to talk around it because they have no way. This object here is an alien beast. That's as alien could be because you're making a number out of a proof. And what's a proof? Okay, you see? And because of that, okay, that is a very important concept which I'm now going to exploit by giving you a little example. Okay, so that's what I'm going to do. All right, so that's the rule. So let me use these two rules to show you something about quantification that I think is important. Okay, are you with me so far? Is this okay? Okay? All right, so let me roll that up. So now I want to talk about something, this is the traditionally at this moment is the right thing to talk about. I'll talk about something called, I'll put it in quotes, the axiom of choice. Okay? And actually what it is the theorem of choice. Okay? And that's what I'm going to do. Okay? There are many ways to formulate what in like traditional. So what I'm going to do is I'm going to portray this to you in a form that makes the traditional accounts look bad because I think the traditional accounts are bad. Okay? So I will explain it to you as follows. Okay? So the traditional account of the axiom of choice, there are many equivalent formulations of the axiom. I'm sure that you could rattle off a dozen of them if you want. But a very basic one is, every total relation, binary relation, contains a function. Okay? So how do you say that? So one way to say it is you say every total binary relation, that's I'll write it out sort of in English, contains a function. So what does that mean? If I have a binary relation R, which is total, that is, whatever its domain is, every x is related to some y. Okay? It's total. I'm going to select from that R a subset, which is going to be a function. So I can write it out like this. So what you say is, okay, if for every x, let's look over a relation over A and B. So if for every x in A, we'll write it like that, there exists a y in B such that Rxy, that's totality. Okay? That's how you would write it out, like in logical notation, right? The relation R is total means for every x in R is relation between A and B. So between for every x in A, y, yeah. Then I do this all the time. Then there exists a y that is related to it by R. That's what totality is. And what you do is the so-called axiom of choice says this implies that there's a choice function. That is, a function which witnesses the totality of that relation, which can be expressed as saying, well, the simplest possible way, I can actually jazz this up a little bit, but the simplest formulation is you look like this, that there exists an f, such that for every x in A, I choose the y, f is the choice function, which chooses the y. So this is called the choice function. Okay, which chooses the y that corresponds to x in the relation R. Okay, so that's what it would be stated as a principle of logic. Say again? Did I make a mistake again? F of x, yeah, jeez. God, I'm really terrible with that. Yeah. Okay, yep. Sorry. Okay, so that's the way. So the statement is sensible, I hope. Okay. Notice, in order to say it, I needed to have existential quantification over functions, because I have to have a choice function is a function, so I have to be able to express that. Okay. So a lot of times this is formulated in set theory, where there's really only one type. It's the type of sets. Okay. And then you work everything inside that one type, and it's a kind of cockamamie way to do things, but it's what you do. Okay. That's the way it's done in set theory. It enjoys all of the deficiencies of any unityped approach to programming or to doing mathematics. You have a lot of codings, and it's really unpleasant. Okay, so the idea about type theory is to just bring out the structure which is there rather than try to hide it. Okay, so here I do that. I bring out the structure that's there by being explicit about the typing. Okay, so I have this. So as you very well know, no matter how the variations of how you formulate this, this is postulated as an axiom of, for example, set theory. Okay? And it's known that it has to be postulated as an axiom by a very complicated argument, which says that it's independent of all of the other axioms of set theory. So you really have to postulate it outright. But it's a weird thing because, and people find it questionable, because it has existential force. Right? It tells us that certain things exist which, so to speak, otherwise don't exist. In other words, if you write down the words, the rules of set theory, and you have a notion of function that arises from the idea of power set and da-da-da-da, and you write it all down and everything looks really good to you, and then you suddenly realize that you've missed some important functions. And so the way you do it in set theory is you say, oh, the hell with it. You just postulate it outright, of whole cloth. You just say, we'll throw that one in there too. Okay? And that's the axiom of choice. That's what you do. Well, that's what people do, and it works for some value. It works. So the thing I want to point out here is that in the constructive setting, it doesn't need to be an axiom. It's actually a theorem, and I think it's helpful. This is a person that's. What I'm going to do next is a purely psychological move that may be helpful or not helpful, which is to think of this as a construction inside of type theory. So it says, I'm going to write down a function that is given an element of the big disjoint union. And what you want to do is you want to think it like this, okay? So it's given this construction. It's given an element of this disjoint union as an argument, okay? And then it wants to deliver back, it wants to produce an element of this disjoint union. Now, all I'm doing is changing the notation. I am, but I'm trying to stress the constructive reading of this. That's why I'm doing that. Okay? If you don't like it, then just ignore this line. It's the same as the previous one. Okay. All right. Oh, did I screw it up again? What did I do now? Too many people talking at once. Oh, yeah, that's a pi x in A. Sigma, yeah. It's weird, I'll tell you. It's hard to get these things right when you're up at the board. Okay, so that's a restatement of what I'm going to do. So what I'm going to do is I'm going to say, I'm going to show you there exists a term m, okay? And I'm going to tell you what that term is, okay? And therefore, I'm going to give you a proof, okay, that this is a theorem. That's what I'm doing. So how do I do that? What I'm going to do is I'm going to define m in sort of the only way you possibly can. So what you do is you say, okay, I'm going to take in as an argument a proof, let's call it T, just because that's what I happen to think of, a proof T that a relation is total. You see, I get the proof as argument. See, that's what's really slick and clever about all of this, okay? Look, you're saying to me, this implies that. When you say this implies that, it means that you have a way of transforming a proof of this into a proof of that. So what I'm going to do is I'm going to write down that code. Okay, I'm going to write down a function lambda that takes in a proof of the totality. And I want to emit, I want to get out of this thing a function. So I'm going to write down here a pair consisting of a function and a proof that works like that. So I need to write down a function here of type A arrow B. So this will be written lambda x in A, something, okay? And then this will be a proof that for every x in A, something or other holds. So this will have to be a lambda, and then this will be something. Will get filled in here. Like, we agree that that's pretty much what you have to do, right? Is I'm going to use t in here somewhere, obviously, but this guy has to be a function, right? There's a existential quantifier here, so I got to show you the function. I'm going to write that down, and then I have to give you a proof, which is a function because it's a for all statement. It's a pi. Okay, so I can write that down. So what do I do? So, well, if you claim to me, what do I want to do? I want to say, given x and a, I want to use this information t to extract an element of b in such a way that b will be related to, that extracted element will be related to a. Okay, that's what I'm going to do. Well, that's pretty damn obvious because I'm given that for every x and a, there is a b. So what I'll do is I'll just take t, take pi 1 of t of x. Did I do that right? Okay, I think I do pi 1 of t of x. Because if I take t, which is a proof of the totality, that's why I called it t, of the relation, and I give it the particular x, it emits, right, the assumption, the proof emits a witness and a proof that it's related to x is related to that witness by r. So let's pull that back out. That's pi 1 t of x. And then what do I do over here? Well, what I do over here is I want to prove that for every x and a that they're related. Well, what do I do there? Well, that's just pi 2 of t of x if I didn't make a mistake. Why? Because the type of pi 2 of t of x, remember, is substitute pi 1 of t of x in for y in rxy, which is exactly what I want. In other words, I want r of x, pi 1 of t of x, and pi 1 of t of x is the result of applying this guy to x. And I believe I am done. Okay? And that is, if I didn't screw it up, that's a correct proof term. So this should be called the theorem of choice. Okay? And that's it. This is a very remarkable thing. What makes this work? Okay? The key is that proofs are mathematical objects. This is what I said to you in the beginning, the very beginning. Well, logic as if people matter. We start out with proofs. We treat proofs as objects in our theory that I'm able to extract. I have t of x as a proof, and I extract an object from the proof. So this is extract the witness from the proof. So what's happening in the usual formulations of the axiom of choice is you don't have access to the proof. So you're supposed to get the F out of nowhere at all. Okay? You're supposed to, the F has to magically appear for no good reason whatsoever, because there's no way to get at what that F is, because there's no way to examine the hypothesis, which is a proof. When you have the proof objects available, you just hack around with them, and it becomes a theorem. So the theory is completely self-sufficient and self-contained and works for general reasons. It doesn't require any kludges, okay, to make it work. I sort of view the axiom of choice in sets as a kludge. Okay, that's what's happening. You wrote a whole bunch of code and you erected this big apparatus, and then something doesn't work, so you kludge in a little fix. Okay, so that's what you do. So it's a kludge. So here, it's not. It works for general reasons. So another way of saying this is, which is implicit in what I'm saying, is the only way in a constructive setting to prove, and this is a little more subtle, I hope I can get this across. Another way of interpreting what's going on here is the only way to prove the totality of a relation in a constructive setting is to exhibit a function. Why? Let's see if I can tell you why. In other words, what I'm really saying here is implicit in the proof of totality is a function. And I'm going to make that function explicit. That's what it is saying. So why is there a function implicit in the proof of totality? Exactly because the rules of quantification tell us that a proof of a universal quantifier has to be functional in X. Why? Because here, you're going to give me a proof uniformly in X, and by the principles of structural equality, this respects equality in the domain. So this defines a mapping. It's a function. So the proof has to be a function that takes X, and for any X, gives us, as a function, this ordered pair. Okay? So the point is that in order to prove for all exists, you must, when you write the proof, implicit in the argument, must be a functional choice. You must have made that choice already. And all this is doing is extracting from the proof the choice you already made. Okay, so that's the critical idea. That's what's really going on. Now there's another even more beautiful idea going on, which I think Steve Audi will talk more about, is that we can interpret types as kind of topological spaces. And then what is happening with the universal quantification is a continuous dependency of the choice of the pair here as a function of X, so that this will intrinsically come out as a continuous function. There will be no discontinuities. Okay? And in fact, one of the beauties about type theory is that the type theory is set up in such a uniform and smooth way that you can consistently interpret the entire thing as speaking about continuous functions over topological spaces. And this has an enormous significance. And we'll say a little bit more about that later. But it's intrinsic in the constructivity. It's the idea, the constructive ideas that I'm explaining to you are what make that whole engine work. Okay? And it's really important to understand that. So I want to emphasize, at least here, the constructivity, and we'll get back to the continuity and topological interpretation later, and its relation to homotopy theory. We'll get to that. Okay, so questions about the so-called axiom of choice? Yes?
Say again what Pi1 is doing.
Say again?
What Pi1 is doing.
What Pi1 is doing is extracting of the existential quantifier from a proof, because T is a proof. I mean, in type theory, I've said over and over, there's no distinction between proofs and not proofs. But if we think of it, I wanted to draw you through it by thinking of it as logic. So if I think of this as logic, then T should be thought of as a proof of a Pi2 sentence for all exists. Okay? And then what I'm doing is I'm writing down a term of a type. Okay? So maybe this is n arrow n. Like, think of A and B as both being the natural numbers, if you like. So I'm writing down a particular natural number that is obtained by running the projection on a proof. That whole concept is completely non-existent in first-order logic and the usual textbook accounts of logic. Look at any of them. There isn't a single one. Okay? Type theory is the only one that gives pride of place to proofs. And that is a thing of beauty. It is the most gorgeous intellectual idea that I know. And its implications are dramatic. Yes?
Sometimes I think people prefer to not have the axiom of choice in the logic.
Well, in set theory they do, but that's because of the problems of set theory. I mean,
okay, so that benefit of
the reason they don't is typically, as far as I know, the people who sort of say don't want it, other than people doing meta theory or like trying to relate various axioms to each other and stuff. Let's forget about that for a minute. Practice, the only reason people would say they don't want it is because it's a bald existence statement that has no justification whatsoever. Okay, you just say, there exists such a function, period. It's a kludge. I mean, it's a recognition of the fact that it's a kludge. Basically, everybody knows it's a kludge. And some people will write out, I can't get this open, and some people will write out in their papers whether they relied on that kludge or not because they sort of feel guilty, in my opinion. It's never been comfortable, okay? But the problem is the set theoretic foundation. They don't really make much sense, okay? And in the long run, that'll all go away, okay?
Can you always extract a witness from a group?
Yes, in the formulation I've given here, you can, because if I can find the board. This is how I axiomatize the sigma type, is that the elimination form extracts it. And I'm strongly emphasizing that this is an unusual feature of type theory. It's only possible because you're in the setting of type theory that you can even entertain the notion. That's the way to think about it here. Okay, so that's what's going on with sigma and pi types, and this is a very good example, okay, about sigma and pi. There are various ways to generalize this. You can generalize it to allowing a dependency here, in which case this would become a pi. So you can do that. That's a minor generalization. Okay, you could do that. I thought I would do something simple first of all. Okay, so that's certainly a form, and there are many equivalent reformulations of this that can be written down and proved. Okay, so good. Another thing you might do is, if you only had this as your elimination form for sigmas, you will fail in trying to give a proof of the axiom of choice. Try to do it, okay, and see why it doesn't work. Okay. Well, yes, the whole theory is constructive. I mean, well, okay, that's a little bit hard to answer, because classical logic is a mode of use of constructive logic in which I postulate as an axiom that all predicates or all propositions are decidable. So in that sense, it's perfectly classical. It's just that when you do something in classical logic, you're using a kludge. Well, the way I would say it is a heuristic assumption. There's a heuristic assumption that it can be helpful to someone. Like I said, if you think about Newton's method is a really good algorithm, but for the fact that you can't actually compare real numbers and tell whether one is less than the other or equal to 0. Okay? So you make a heuristic assumption. You say, let's work under the convenient assumption that the real numbers are, atoms that are discrete, that we can compare and treat them like data, and now let's work under that assumption. That's what, and then the justification for Newton method is exactly that. Okay? Yes?
I'm trying to relate something I don't know. So, is what you're saying, okay, now that we're using heuristic logic, we have witnesses for exist. We always have a witness
Yes.
for exist.
Yes.
And so we can use it.
Yes, that's right.
Okay, and this works, you said that only works in type theory, but I guess it also works.
No, this is type theory.
Yeah, but I guess it works in corresponding logic, right? Intuitionistic logic.
Yes, that's right.
So
Yes.
we can also prove the axiom of choice in intuitionistic logic.
If intuitionistic logic is formulated as type theory. Okay. I know you're finding it. I know. I'm trying. Okay. My explanations are partly based on the assumption that you've seen other treatments of logic. I don't know whether you have actually. Okay. If you look in the textbook treatment of even intuitionistic logic, it is not done like this. And then it's a... Okay, it doesn't work properly. What's that? You won't be able to do this. This move will not be available. Okay, so if you took a version of logic, if you tried to write down, so here's the exercise. If you tried to write down the rules for a kind of first-order logic, let's say a multi-sorted first-order logic, even a single-sorted first-order logic, where you quantify over one or more types, and you write those rules down, one of the rules you'll write down is the one on the left-hand board in orange. Okay, because that's what it will look like in a ordinary textbook formulation of logic. You will not be able to carry out the derivation in that formulation of logic. What's that? Because it's broken. Because it's broken. Okay? Because you cannot fully express the inversion principle. The idea is that the rules I've given here fully express the ones that are now obscured on the board, the sigma rules, are fully expressed. They invert the introductory rules. That is the proper expression.
You're saying that the elimination rules that they use
Are broken.
are not complete.
Yes, they're broken. Yes.
But those are not complete.
They're insufficient. Yes, that's right. They're not, yes, that's what I'm saying. Right. And the reason is, in order to express them properly, requires a radical move. You have to change the way in which logic is done so that the proofs become objects of the theory. And then you can formulate logic properly. And this is what Brouwer was saying back in the 30s, that logic is just a branch of mathematics, whereas everyone up to that point was saying you derive mathematics from the principles of logic.
Just to make sure I understood, so you're saying that, okay, if you have some intersection problem for which, you define the rules for the quantifiers, and the rules are local bound and local complete, then we can derive that connection.
Yes, you will be able to, but the conventional formulation will not be, as they say, locally sound, locally complete. That's the point. Okay. They don't